So we have been talking about space, which is exciting for me. I think I've unilaterally declared this is like my new favorite thing to teach. I've never taught before, and I like it. Yesterday we talked about the life cycle of a star, right? And we talked about where they come from. How does a star start off? What does a star start as?
As dust.
Yeah, just as a big cloud of dust. What happens to that big cloud of dust?
It starts moving in on itself, and the friction makes it hot. So
Good. So why does the gas move together? What makes that happen?
Because there's no gravity in space.
Well, there's no big source of gravity, but there is gravity, specifically gravity between these dust particles, right? So they pull each other in just due to gravity. And as they form a bigger clump, they have more gravity, which causes more dust, which gives it more gravity, which causes more dust. And like, I can't remember who said, but somebody said, as that happens, these particles are rubbing up against one another, which makes them hot. They get hot. So eventually, they get so big and so hot that we call it a star. It's just a big ball of gas. What is that gas overwhelmingly? What are stars mostly made of, especially when they're young? Young stars are made of what? Yeah. Hydrogen. Good. And those hydrogen atoms get so packed together, they end up slamming into one another, and they become helium. Good. And that's a nuclear reaction. That releases incredible amounts of energy. How do we experience that energy that it releases?
Sunlight.
Sunlight. Yeah. Right? You've all been to the beach. Like, think that the sun is so incredibly far away, and yet from all that distance, it's warming you up. Imagine how hot it would be up close. Has anyone ever been, like, I don't know if anyone like has family live on a farm, or my wife grew up on a farm, and they would always have a brush pile on the go. Does anyone, the idea just basically being if they trim something off a tree or if they've got leaves or whatever, they just make a big pile. And then every once in a while when the pile gets too big, what do? Yeah, you pour some gas on it, you throw a match on it, and you burn it, right? And like if you live in the country, like everything goes on the brush pile. Old couch, brush pile. Seriously. Like, oh, old bed, brush pile. Like just cardboard, brush pile. Just everything goes on the brush pile. But have you ever been around a fire that big? Where it's weird because I always remember the thing that comes to mind me once was driving on my school bus. I went to school in St. Catharines, but I drove in from Niagara. And so we drove like by like through Niagara on Lake, like the country area there. And I remember driving by a big brush fire once, and it was pretty far away. But as the bus went by, it was like, whoa, that's really hot. And then we were gone. Like even over that distance, you could feel the heat just for a second as the bus went by. Now imagine with the sun, we're talking about that same effect, but over a massive scale. So this thing is really hot. Our star is, I can't remember, it's on your diagram from yesterday, but is it what, 5,700 Kelvin? 58? 5,800 Kelvin, right? Which makes it about 5,700 degrees Celsius. That's really hot. That's very, very, very hot. Now, having said that, even though the star is a lot of hydrogen, eventually it uses up its hydrogen. When that happens, what will happen to that star? Well, before it could, when all of it's used up, it could. But before that?
It turns into a red giant.
Yeah, so as it's starting to use up all of its hydrogen, it's mostly helium, it actually expands. It gets a little bit cooler. Now, I mean, it's still pretty darn hot, but it's cooler, and it expands, and we consider it a red giant. And a red giant's much bigger. When our sun becomes a red giant, roughly how far will it spread out? Yep, beyond Earth, beyond Mars, all the way up to, Connor? All the way up to about Jupiter, yeah. So it's going to be real big. And then that's a pretty quick phase. And now for our sun, which is a typical sun, what will happen when it uses up all of its hydrogen, right at the end of its life cycle? Anyone remember? Yeah, what do you think?
Oh, shoot.
It's okay.
It turns into a white dwarf.
White dwarf. Which means that it does what? That big star becomes... It collapses in on itself. And now it's not undergoing nuclear reactions or anything like that. It's just all that friction of collapse makes it really, 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 really hot and bright. But there's nothing fueling it. So over time, what will eventually happen to that white dwarf?
It'll become a black dwarf.
Yeah, eventually it'll actually cool down. Eventually it will stop being a star, and it'll just be, well, it won't be a star as we think of it anyway. Now, interestingly, that takes so long to happen that the universe isn't old enough for that to have happened anywhere yet. So if our understanding of the age of the universe is right, there can't be any black dwarf stars out there because it just hasn't had time to happen.
How do we know when we become a black star if we've never seen it happen?
Because we can do the math. And that's the amazing thing, right? Most of these things were predicted by the math first, and then we found them, which I cannot stress to you how incredible that is and how cool that is, right? Like, we make these predictions and then we find them. And sometimes we turn out to have done the math right and we're right. And sometimes we go out looking and we find things and it shows that we've done the math wrong and we were incorrect and we have to change our theory. And we've had lots of both experiences. Science has lots of experience going, hey, we made a prediction that was right. Look at us, aren't we clever? And science has lots of experience going, hey, we made a prediction and we were totally wrong. And they're both good. They're both learning. They're both the process of learning. I would argue you learn a lot more by being wrong than you do by being right, but it feels a lot better to be right. Now, that's the life cycle of our star. But if a red giant is a really big red giant, if it's a big star that's become a red giant, what will happen to it when its hydrogen gets all used up and it goes to collapsing on itself? A supernova, which is what? I saw your hand, sorry. What's a supernova? Yeah. It's all the matter of that star just being so big that it can't collapse in on itself, and it just, huge explosion. Right? Really, really, really bright, really powerful. We can see them from far away. And then that will do one of two things. It will collapse down to be a really special kind of star, a tiny, tiny little star called a neutron star. A neutron star is so tiny that the atoms are actually next to each other. Like the nucleus of the atoms are next to each other. So there's no space between the atoms. And remember, normally an atom is all empty space, but they're just lined up nucleus to nucleus to nucleus. They're really tiny. And if it's even bigger, we don't get just that, but we'll actually collapse even further in form. Yeah, nice and loud. A black hole, which is all of that mass collapsed to an individual point, just collapsed right in on itself. So far collapsed that it breaks our general understanding of how physics and chemistry work. We call this a quantum singularity. And if you take physics all through high school and then some university physics, eventually you'll learn about it. And hopefully you'll do better in that class than I did, which is all I will say about that class. But it's really interesting stuff. So that is the life cycle of stars. Today we want to talk about planets. Because luckily for us, we didn't just get a star forming, we also got planets. Okay, so let's talk about that. This is going to start off looking a lot like yesterday's note, because planets can only form where stars form, all right? We only get planets if there are stars. And you're going to see why. At the end of this, we're going to define a planet, and you'll see why. So how do the planets form? Well, it starts with dust again. All right? So stars form dust. As stars form, they rotate. All right? The sun, or any star, as it's forming, begins rotating. And interestingly, as it rotates, the dust around it rotates. Yeah. So as that central mass starts spinning, all the dust around it that is making the star also begins spinning. And an interesting thing happens in zero gravity when you do that, which is a ball of dust, as it spins, will actually flatten out to form a disk. It'll actually flatten out to be a disk. By the way, we've seen this on the small scale, because just like all the dust around the sun did that to make what we call an accretion disk, this is how the rings of planets form. So if you look at Saturn, Saturn has rings. Venus has rings that are less visible. I think Uranus also has rings that are much less visible, but Saturn has the really big, beautiful, visible ones, right? That is just dust that was spinning around that planet as it spun. And when you spin a ball like that, it naturally wants to flatten out along the plane of rotation. And so that happened. So we go from a ball of dust to a star forming in the middle and getting this disk around. And as we mentioned yesterday, that disk is called the accretion disk. And I think yesterday I spelt it with one C because I'm silly, but it's two. Now, the neat thing is this. Most of that dust, the overwhelming majority of that dust, ends up getting sucked into the sun itself and becoming a part of the sun. Does that make sense? But some of the heavier stuff, so some of the heavy dust, before it gets sucked into the sun, will start colliding with other heavy dust and forming balls right out there in the orbit. They'll start to form spheres. And then a snowball effect happens, where just like the sun, the bigger that ball of rock gets, the more gravity it has, the more stuff it attracts as it spins through the accretion disk, and it builds and builds and builds. And slowly that little ball of rock becomes a bigger ball of rock, becomes a much bigger ball of rock. And if this keeps happening, eventually it will pick up all of the dust in its particular spin around the sun, and now it's a really big ball of rock that we call a planet. So that's how the rocky planets form, where as these rocks collide, they start to get bigger and bigger and bigger. And before you know it, they're big enough and heavy enough that they can have a stable orbit. And instead of getting pulled into the sun themselves, they develop a stable orbit around the sun, and they get bigger and bigger. Yes, we'll go one at a time. Yeah. They don't get pushed out. All of that gas is already out there, and all of that dust is already out there. And as they spin around, they just stay where they are, but they accumulate. Does that make sense? Good question. No, because there's not enough mass there. And we're going to talk about that. This only works if there's enough rock there for these to start building. And it's really interesting. And some of the physics is beyond where we're able to go with this. But planets can only form in really specific places. So there's a famous scientist named Johann Kepler, and he studied the orbits of the planets. And what he found out is that there's this incredibly pure mathematical ratio of how far the planets are from the sun. They occur in very predictable, repeatable places. And that has to do with the relationship between the gravity of the planet itself and the gravity of the sun. It's pretty complex math. We're not going to get into it, unfortunately, though there's a grade 12 space science class that you can take at the DSBN. They usually offer it just online, and it covers that. And as Rochelle can tell you, online courses are wonderful and a very valuable educational experience and a great way to learn. She really enjoys all 3 of her online classes. Anyway, I've said too much. Yes? Yeah. In fact, our planet gets heavier every day. A little bit bigger, a little bit heavier every day. And we talked about this in our Unit 1, ecology unit, right? Yeah, that's right, because we have gravity. That's right. So eventually, some of the gas and dust in the accretion disk collides and begins to snowball. And I want to be clear, snowball is not exactly a scientific term, but it's a really good term for this, because we all understand how building a snowball works, right? Like if you're making a snowman, which is you start with a little bit, and then do you have to keep packing the snow on yourself? No, you just roll this thing, and it just attracts more and more and gets bigger and bigger, right? Building a snowball is very similar to how the planets formed, which is once they get to a sufficient mass, just moving through space, they pick up that extra mass and pick up that extra mass. And because that is revolving, just like how you roll the snowball through, it picks up mass in an equal manner. So it gets bigger and bigger while maintaining a shape. And if you make a really nice snowball, it makes a nice spherical shape. Mine never did. Mine always looked like rolls of sod, right? Like they're round in one direction, but I've been too lazy to roll it the other direction, so it's like flat on each side. Maybe you've had this problem too. Anyway. The great thing about, like, at a certain age, you become a parent, maybe. I mean, if you choose to. Maybe you will, maybe you won't. But when you do, like, your kids want to do these things, and you can pretend that you're, like, begrudgingly making snow forts and snowballs and snowmen with them, but really it's just super fun and exciting for yourself. And you're like, forget marking. I'm making a snowman. Anyway, it's the end of my story. So eventually some of the gas and some of the dust, it starts to collide, and as it orbits the now forming sun, just as the sun is, and it is different, right? It's different because the sun is pulling new mass towards it by gravity, right? But these are different. These are getting bigger, not primarily yet by just pulling things into them. I mean, it's a little bit of that. But it's also that they're spinning around, and as they're spinning around, they're collecting new material and getting bigger and bigger. Can you imagine that? So this is happening at the same time that the sun is still forming. The sun is not fully formed yet. Does that make sense? So the planets develop as the sun develops. Now the sun is already big and bright and beginning to be a sun, but there's still lots of dust, still lots of gas in this. And you can see kind of a diagram of that here. We start with just a ball of dust. It starts to collect in the center and spin. And remember, viewed from above, our entire solar system spins counterclockwise, right? So if you went to the North Pole and moved up and looked at our solar system from above planet Earth, if we think of North as up, which of course we do because we live in the Northern Hemisphere and we're egocentric, you can rest assured that if white people had lived in the Southern Hemisphere, South would be up. But anyway, white people, we're the worst. No, I'm just kidding. All people are the worst. And slowly as that revolution starts to happen, we get these balls of dust close to the sun and gas far away from the sun. We'll talk about why that's different later on. Starting to get bigger and bigger. But they're not planets yet. They're kind of planetoids. They're just getting bigger and growing. As it continues, they're still collecting dust and going and going. And then eventually, most of the dust and gas are collected either into the sun itself or into the planets, and we get our solar system. Now, to be clear, our solar system still has plenty of dust, plenty of rocks in it, plenty of gas and things like that. We have an asteroid belt between Mars and Jupiter. We have an asteroid belt outside of all of our planets, which we call the Kuiper belt. And surrounding that is an enormous cloud of dust and particles and gas that we call the Oort cloud. Isn't that a lovely name? So, I mean, our solar system still has lots of kind of junk in it. But most of the material has collected either into the sun or into the planets. That kind of makes sense? And we call this process accretion. Accretion. A-C-C-R-E-T-I-O-N. Now, there are other things. So about 4.5 billion years ago, which is right in the early stage of development, you could actually get multiple planets forming in a single rotation. Does that make sense? It's not like just one ball of dust will start to snowball. You could imagine that if this whole class went out to a field and started making snowballs, we would have 33 snowballs, right, with everyone who's in this room. But let's imagine that we were just blindly going, and let's say some of us are doing this really quick, and our snowballs are getting big quickly, right? And then other people are a bit more deliberate, they're going a bit more slowly, maybe some people are texting, and those is very small. And I'm pretty competitive, so I see like mine's getting pretty good, and I see Richard, and I'm like, oh, Richard's barely started. I'm just going to barrel right over his. And now his snowball is part of my snowball. Does that make sense? So you would get multiple planetoids forming in the same kind of area at the same time. That's very normal. And some of the smaller ones, well, what might they end up being? What do you think? If they're really small, definitely. And that's what we think some of our asteroids come from. Some we think came from outside the solar system, and some we think came from the formation of the solar system. Yeah. What else might smaller planetoids end up becoming? Moons. Were you going to say the same?
I was going to say dwarf.
Yeah, they could be dwarf planets, definitely. But the ones that share our orbits, if you have a big planet forming and a smaller planet forming, if they come together the right way, the one might end up orbiting the other. And you get the big planet ending up as the planet, and the smaller thing ending up as a moon. Our moon, interestingly, we don't think formed quite that way. We think it was a bit more dramatic. In fact, we have very good evidence that it was more dramatic. There was a second planet that shared Earth's orbit, or a second planetoid. So we had Earth, and they had this second planetoid that they called Theia. And we think that Theia didn't end up orbiting Earth. Theia ended up, colliding with Earth, smacking right into it, which is an incredibly, incredibly, incredibly violent collision. All right? When two things that big collide, you're talking about massive amounts of energy. And in the process, most of Theia's matter ended up as part of Earth, but parts of Theia and Earth together ended up being ejected into space, and they formed, at first, just a big cloud of dust and things like that were orbiting Earth. And then just like our planets formed, orbiting around the sun, all of this ended up collecting itself as it orbited around Earth to form the moon, or as Dr. Mitrovic would say, moon. Yes?
Why do you name our moon the moon and not some cool name like the other moons?
Because our moon, for a long time, as far as we knew, was the only moon. Right? Because when all we could do was look with our eyes, the only moon we could see. And even once we knew there were other planets, does anyone know who the first person to see a moon that didn't orbit Earth was? You may have come across this. Galileo. Yeah, Galileo with his own hand-built telescope. Is that true? I might have made that up. We talk about Galileo's telescope all the time. I have no idea who built it. What am I talking about? I'm just making stuff up now. For some reason, I have it in my head he made his own telescope. That might be true, or I might have invented that right now, and that could be exactly not true. And to be clear, I have no idea. That was absolutely fake news. This Breitbart moment brought to you by Mr. Orlando. Anyway, he had a telescope. Somebody built it. Could have been him. Could have been someone else. Could have been China. I don't know. Anyway, he was the first person to ever see the moons of another planet, and he made observations of them, which is pretty cool. Pretty cool. So within these orbits, we have collisions of different bodies, and they may do things like just make the planet bigger. In other words, we have craters and such like that all over our planet that are the result of collisions. But if you get a really big collision, you could actually get the formation of something like a moon, where you get this big cloud of dust out here that is destined to become a moon. Does that make sense? And then keep in mind, like, the moon's surface isn't perfectly round either. It's full of craters and things like that. Because just like Earth has dust that collects around it and gets attracted to it, Moon has dust around it, and asteroids and comets around it that are attracted and fall into it. Does that make sense? So it happens on the same scale. Exactly what is happening to the sun happens to each of the planets, just on a smaller scale. Pretty neat. So what are we going to say about this? We're going to say planetoids in the same orbit as larger planets often ended up as moons or colliding with the planet. I got to replace this pen tip. I'm writing like a 3-year-old.
Yeah, they're pretty.
Our moon formed as the result of a collision. Maybe you don't need to write that if you can see the diagram above. That's your call to make. But I've written it. I said this last period, but they say the trick to being British is being surprised every day when it rains. I think the trick to teaching the way I teach is being surprised every day when the technology doesn't work the way you want it to. Every day I'm like, oh, it always works, but really it doesn't always work. Actually, it usually doesn't. But anyway, I'm having trouble zooming in and zooming out today. Not feeling very responsive. I've got the wrong pen tip on my pen and it's stressing me out, yes? Yeah, so that's another example. Now that's much later on. So this collision that formed our moon was massive and about 4.6 billion years ago. And that was an asteroid the size of a planet, about the size, they say, of Mars that struck, like, that wasn't an asteroid, it was a planetoid that shared Earth's orbit that was massive, that collided with us. The asteroid that we believe hit the Yucatan Peninsula and we believe destroyed massive amounts of life on Earth at what we call the KT barrier, so at the end of the Cretaceous period, was a few kilometers wide. So I mean, big, but nowhere near this scale. So we're talking about something like the size of Manhattan, like, you know, the size of like New York hitting Earth, and it wiped out most of life on Earth. Now imagine something the size of Mars. Had there been life on Earth when this happened, which we don't believe there was, we don't believe there's enough time in the early, we don't believe there's the right conditions on Earth in the early planetary stage, but had there been life on Earth when this collision happened, it surely would have been destroyed. You're talking about a collision so massive that the Earth would have become hot enough that most of the rock on the surface would have been liquid or gas. This is a massive, massive collision. In fact, we believe a lot of the matter from the asteroid that hit the Yucatan Peninsula actually became gaseous rock. Imagine rock getting so hot. It becomes not just liquid magma, but there's actually a gas that can expand. And because it was a gas that could expand, it could surround the whole Earth very quickly, because gases move quickly. And then as it cooled back down, it became red hot magma coming down to kill everything on Earth. We believe it to have been a really, really, really disastrous event. And it is millions of times smaller than this collision. Just a good sense. Great question. Yes? Yep.
Before they crashed, the Earth was spinning straight after.
Yeah, no, that's actually, I'm glad you mentioned that, because I was going to mention that on the next page. But the other thing that these collisions serve to do is that they served to put things off axis. So we believe that one of the reasons Earth is at a 23.5 degree angle, which, what does that give us, by the way? It gives us our seasons, is because of the collision with Theia. In fact, we think it tells us that we can figure out what direction Theia struck us from, because of the angle we are. Yeah.
When Theia crashed into the Earth, did it hit the atmosphere or did it go farther from that?
Oh no, you're talking about serious collision. It would have, like, again, because Moon is made from a combination of rock that would have been Theia and rock that would have been Earth before. So you're talking about a collision that results in massive amounts of both planet Earth and planetoid Theia ending up in space and orbiting around and collecting. Yeah, good question. What's going on? I'm just going to work this way. Yes?
Is there like remnants, like of the crater or whatever from the hit?
Interestingly, A, we were talking about such an early formation that there have been so many collisions since, but B, this was so massive again that much of planet Earth was, the models show, would have literally been liquefied. And the interesting thing about that is we know that a liquid will actually settle out to be kind of smooth. So if anything, it actually would have had kind of a smoothening effect on it, where it was so forceful that you would have actually ended up with a really big distribution of rock. That's a very good question too. And again, I should point out, I am by no means a scholar in like early solar system formation. So this is based on my limiting understanding of what I've read. And there's a lot more to read than what I have. And it's a really interesting topic. So if you're curious about it, I encourage you to seek out more resources. I'd be happy to help you do that. But my understanding is this particular one is not something we should be looking for a crater for. It is actually so forceful that we think of it as not only the thing that formed the moon, but really something that had a lot to do with the formation of Earth itself. Earth was fundamentally different after this collision. Yes? Oh, good.
Why didn't Earth have a crater after?
So the same thing I just said there. Such a big collision that it really just massively reshaped the Earth itself. Also keep in mind that 4.5 it's saying. Our solar system itself is about 4.8 billion years old. So this is very early in the life of the solar system. A lot happened to Earth after this. I mean, if you look at the diagram of Earth, it looks nothing like our Earth. There's no liquid water on it yet. A very, very different place. Yes?
Why didn't it knock off the orbit? Like, why didn't when the collision, why didn't it knock Earth away?
I'm sure it probably changed Earth's orbit. I don't know about that, but my prediction would be that it would change Earth's orbit. Don't forget, the gravity of Sun is massive. So would it have changed Earth's orbit? Certainly. Would it have given Earth enough velocity to just escape the gravitational pull of our Sun? No. That makes sense? Yeah. Think of it this way, like if two cars collided and they're just driving down the highway, they're going to collide and they're going to stop, right? But if you had those, have anyone ever been to the airport and they have those moving sidewalks? This is just what I want in the hallways here, where you just stand and the hallway moves for you. So now imagine if you had two toy cars and they collided there. They would shift, but they'd still just keep moving with the moving sidewalk. Does that make sense? You can kind of think of the sun's gravitational pull on us as that moving sidewalk. It's got enough force to just move us along. Would it have maybe moved where we are in that movement? A little shift to the left, a little shift to the right. Would our orbit have gotten maybe a little bigger, further away from the sun? Yes, but it's not going to knock us away from our orbit.
Maybe that's why our orbit's weird.
Planets with more than one moon, will they ever hit?
We postulate that moons can collide. Basically, we think our solar system is old enough now that most everything is in stable orbits. So certainly our planets are in stable enough orbits that if they were going to collide, they would have collided a long time ago. Same with, we believe, all of the major moons of the major planets. But lots of smaller stuff is constantly colliding in our solar system. Great question. Yeah.
What is Saturn?
We're going to talk about that actually, but basically, it's the same idea here. It's basically a combination of gas and dust and bigger rocks, which, keep in mind, is the same thing that the planets were originally formed from. We believe Saturn's rings are an example of the basic setup you would have for moon formation, but there wasn't any one object that collided and got big enough to begin the process of forming a moon in that particular rotation. Yep, but not in that disk. Likewise, there are planets around the sun, but we also have an asteroid belt. And so we believe that asteroid belt is an example of the conditions that could have caused planet formation, but no one thing got big enough to begin coalescing into a planet. So the snowball effect relies on starting with something. Just like you can't start just pushing snow to make a snowball, right? You have to start by making a ball that's at least big enough to get things going, right? Does that make sense? You can think of planet formation in the same way. You have to have at least one big enough collision to give you something big enough to start the process of planet formation. Yes?
Would it be possible for things to orbit the moon?
Yeah, definitely. I mean, we have orbited the moon, right? We sent a spaceship to the moon 6 times. Well, actually, no, to orbit the moon about 10 times. And yeah, it has enough gravity for things to orbit it. Yes. So here's the one other thing I want to mention. Some planets are formed of rock. Others are made of gas. So if in the accretion disk, if that orbit was populated with lots of rocks and dust, what kind of planet is going to form? A planet made of rocks, right? All that rocks and dust will coalesce and make a planet that is rocky. On the other hand, if a part of the accretion disk starts snowballing, but the only thing there is gas, what's that planet going to be made of? So, the part of the accretion disk near the sun was full of rocks and dust. Planets that formed here are rocky. Lowercase r, of course. They're not named rocky, but they are made of rock. Further away from the sun, we had gas and dust. I don't know what you're talking about. All right, all you Latin scholars, what is the Latin word for soil or rock? Anyone know? Geo is Latin word for earth. This is good. Lithio is specifically for rock. Good, but not the word I'm looking for, but good. I'm impressed. Terra! Oh, $1 million prize. Well done. So we call the rocky planets the terrestrial planets. If you've heard the term on terra firma, on firm ground, terrain, yeah, so the terrestrial planets. Of course, when we say something is an extraterrestrial, we mean it is from outside of Earth. Yeah. Okay, I'll give you guys a minute to write that. Yes, ma'am. Yeah, of course. Oh, okay. All right. Yes. I'm not going to tell you because there's a video I want to show you guys a little later about exactly that thing. It's a good question. Yes. We're going to talk about that in about 4 seconds. Okay, so before we get going, we said that when the accretion disk was forming planets, the part of it that was close to the sun was the rocky part of it, and these make the terrestrial planets. So which planets are rocky? We know that at least one, because we're on one. So Earth is definitely a rocky planet. We have landed a rover on Mars and taken pictures of it. So it's rocky. What else? Sure, the moon is rocky, not a planet, but rocky, definitely. Venus, good, and Mercury. Okay, so the terrestrial planets, hey, who knows, if I were to draw the sun in this picture, I mean, obviously none of this is, the distances aren't to scale, but where would the sun be in this picture? Over here or over here? So over here? Yeah. I think I agree. Yeah, I agree. Look at me. So with that in mind, what planets are we looking at here? What is this planet? Mercury, good. Mercury's little, it's close to the sun, it's really hot. What's this one? Venus. Venus is so fascinating. Venus's atmosphere is made of sulfur dioxide, So Venus's atmosphere is basically just acid. Yeah, it's pretty crazy. It's cool stuff. Lovely. And I mean, let's just say all the planets look cool, but it's just amazing for how cool all the other planets look. Earth just looks gorgeous. Like, it's just, we are definitely the best looking of the planets we've found so far. That, you know what, that's true too. Neptune does have a nice look to it. And here we have Mars. All right. These are the terrestrial planets. These are the terrestrial planets. They are all rocky because when the solar system formed, the material that was close to the sun at that time was rocky. And so as accretion took place, as that snowballing effect took place, we get the formation of the terrestrial planets. Yes? Is Mars closest to the sun? No, in order.
No.
Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. And then poor Pluto. Okay. And what do we have here? These are the gas giants. The gas giants. So when these planets formed, they were in part of the solar system where the accretion disk was full of largely gas. And so they're made largely of gas. Now, the question was, do they have a surface? They do not have a surface the way we think of it. They are a big ball of gas, but, and this is important, they're under so much gravity that that gas is so compressed that it has the density of like much more dense than concrete. It's gas, it can move freely, but it's incredibly, incredibly dense. Yes. So like now, you couldn't walk on it because the gravity of the planet would squish you and you'd die. But if you weren't busy being squished and killed by the gravity of the planet, it is more than dense enough to walk on. All right? In the same way that a helium balloon naturally wants to float above, lighter gases. But now imagine, have you ever tried to like pull like a balloon or a life preserver way underwater? It's hard, right? Even though water should just move out of the way, the thing naturally wants to move up, right? Because the water is much more dense than the thing there. Here we're talking about gases so dense, you couldn't make a dent. You wouldn't make a divot. All right? They're very, 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 very dense, despite the fact that they are not, in fact, solid. They are gases, but you can't think of them as being like the air we are in. The air we are in is a very, very low-density gas, which is nothing like these. Yes?
So just say you went down there and you seemed to be immune to the crushing gravity.
Yes.
You could take something and take out the gas. Or is it too dense?
I don't know. I have no idea. I can't answer that question. I'm sorry. I just don't know. I don't. Again, like, it's still going to behave like a gas, not like a solid. Why doesn't it just float away? Gravity. Just like our atmosphere doesn't float away. What planet do we have here? Jupiter. I need to mention, the last ones are nicely drawn to scale. These are not nicely drawn to scale. I wish I'd noticed that before I gave you this picture. What is this fella here with the rings? Saturn. Uranus. And Neptune. That's not a very nice thing to say to me. Okay, so there we have the terrestrial planets and the gas giants formed during the formation of our solar system. Is there anything more I wanted to say about that? There's not. I just left an awkward space there. Because our next thing I just want to mention is this. I've shown you the inner solar system here and the outer solar system. During their formation, the planets would have had essentially perfectly circular orbits. Why would they be slightly off kilter later on? Collisions and interactions with other things. In other words, one of the things we need to keep in mind is that as planets orbit, not only does the sun pull on them, but the other planets also pull on them. Does that make sense? And over time, we developed orbits that are nearly perfect circles, but are not perfect circles. If you look, the biggest offender is which? In the inner solar system? Mars. Mars has a more highly elliptical orbit than most. All right? So most planets orbits are almost circular. And I'm going to say all are slightly elliptical. And does anyone know what the word elliptical means? Does anyone know what an ellipse is? Elliptical. That's an eclipse? No worries. An ellipse, what's the more common it's a shape. And the more common word we have for that shape is oval. Good. So elliptical just means oval shaped. The actual mathematical term for an oval is an ellipse. An ellipse, yes.
What do you call a work that machine is?
Because if you watch the actual gear mechanism of the machine, it moves like this. So it forms an ellipse. Some, cough, cough, Mars, are visibly elliptical.
Why are they all like perfect?
We're going to talk about that. So, and then if you notice, in the outer solar system, the planets all have beautiful circular orbits. Like Jupiter, Saturn, Uranus, and Neptune are very close to perfect circles. Pluto is crazy. And Eris, by the way, is another dwarf planet. Yep. Yes. Now, the good news for Neptune and why they're not going to collide is even though they intersect that way, they're at slightly different angles to one another. So they're not actually in danger of collision. I looked that up myself. I was curious. Yeah. So they are slightly off angle to one another. And so their orbits intersect like if you look just from above. But if you looked in 3 dimensions, their orbits don't actually intersect. Good question. Good thing to know. Yes? Again, at a cockeyed angle that we don't think. Yes.
When they shoot like they're gonna be able to see Neptune?
You might be able to see Neptune in the way that we see the other planets, which is like they look like stars, but they don't move like stars. We're going to talk about that, by the way. How did the early astronomers, with nothing but their bare eyes, know that some of the things they saw in the sky were stars, but some of the things they saw in the sky were planets? Pretty cool stuff. And we'll talk about why they knew that. And when we do, we'll talk about that question you just asked. It's a very good one. Now, why not Pluto? Or poor Eris. And, we never hear about Eris. And Eris is bigger than Pluto, by the way. Bigger planet. And, people are all sad about Pluto, but nobody's sad about Eris. Nobody's like, hey, why isn't Eris a planet? Everyone's like, oh, Pluto. And I'm sure Eris is just spinning around the sun going like, hey, guys, look at me. Look at me, mom, dad. And I'm like, I'm just trying to mark. What do you want? No, I would never do that. Anyway, so Eris is like the poor ignored planet.
It's the less successful.
Oh. Okay, so anyway, this is a note. Like, not this is note, but this is a thing of note. Let's say, note bene, note well that. The reason we don't consider Pluto a planet, and the reason we don't consider Eris as a planet, is because there's actually a ton of things like Pluto and Eris orbiting our sun. we have a lot of dwarf planets. I think we've identified 5 of them. But we have reason to believe there's a lot more than that. All right. So at some point, when we first started finding planets, it was as simple as this. Hey, is there a big spherical thing orbiting the sun that we can find? Hey, that's another planet. As our understanding of our solar system grew and evolved, we had to set up rules for what makes something a planet. And we have rules 3. So rule 1. So all planets do the following. All planets. What's the first thing we notice about all the planets? What do they all do? Yeah, they move around. Very good. They move around the sun. So all planets orbit the sun. If you don't orbit the sun, you don't get to be a planet. So is the moon a planet? No, because what does it orbit? Earth. Now, Earth is orbiting the sun, but the moon is orbiting the Earth. So it's not a planet. It's a moon. Good question. So that's the first rule, which is if you don't orbit the sun, you're not a planet. If you do orbit the sun, you might be a planet. But let's not forget, the asteroid belt orbits the sun, and it's not a planet. And we've sent some satellites up, and they orbit the sun. They're not planets. So the second rule is this. All planets form spheres under their own gravity. They form spheres. So if you look at an asteroid or a comet, it's a rocky thing, but they're irregularly shaped. Yes? Yeah. We have pictures of asteroids and comets. I should have put one on here, but I didn't. But they are not spherical. But somebody asked, why do these things make a sphere? Because eventually, when it gets big enough, any new material it collects is trying to get as close to the center as possible. Can you picture that? Because eventually the center of that planet has a lot of gravity and it's pulling things towards it. And any new material it collects is going to try to get towards the middle. And what shape has everything as close to the middle of something as possible? Triangle. In 3 dimensions, it's a sphere. It's the most compact possible shape. So free of outside gravity, everything naturally wants to form spheres. On Earth, if we release a drop, it makes like a sphere, but then it takes that teardrop shape, right? Because gravity is pulling it down and this part trails. But if you release water from a dropper in space, it will form nice little spheres. Does anyone ever watch those when you're in elementary school? Did you watch like Ask an Astronaut videos with Chris Hatfield? I'll show some tomorrow. They're super fun. It's like, how do you brush your teeth in space? How do you this? How do you that? And they're really cool. But yeah, in low gravity, if you release water, it makes a sphere. A sphere is the most naturally efficient shape possible. But it only works if you have enough gravity to make that shape happen. And for rocky planets, our math tells us basically anything about 500 kilometers across or bigger will start to naturally form a sphere. Anything smaller than that will kind of stay jagged and irregular shaped. It doesn't have enough gravity to really change its own shape. That make sense? So a planet can be considered a planet if it's big enough that it will actually become spherical. It's actually heavy enough that its gravity will deform its shape until eventually it becomes basically spherical. And the Earth, by the way, is basically spherical. Yes, we have mountains. Yes, we have valleys, this and that, but it's basically spherical. In fact, if we have time, and I hope we do, I'm going to show you a little video about that right at the end of class. So all planets orbit the sun. They form spheres under their own gravity. Now, I would note that Eris and Pluto orbit the sun, and they form spheres under their own gravity. They satisfy both of these rules. If you take a picture of Pluto, and by the way, we have just recently, in the last year, NASA had a mission that finally got to Pluto and took pictures, and the pictures are incredible. Pluto is, I'm going to in about 2 minutes. Pluto is absolutely beautiful. It's an incredible, incredible thing, and it's spherical, and it orbits the sun.
Better than
So why isn't it a planet? Rule 3. Nope, not atmosphere. Plants don't have to have atmosphere. Plants don't have to have rock. They can be solid gas. But here's what they do have to do. Planets must, well, I guess I already said all planets. They do something that scientists have termed clear the neighborhood. Earth, early in the solar system development, shared its orbit. You could also call this clearing its orbit. At one point in Earth's development, it was just one of a bunch of big things in its orbital path. But over the course of its development, it absorbed all of that material until the only big thing in Earth's orbit is Earth. The only other big thing is the moon, but the moon orbits the Earth. Does that make sense? In other words, as we go through our orbit of any appreciable size along that path is Earth. There's no asteroid belt that we go through. We've absorbed all of that a long time ago. Do individual asteroids interact with Earth? Sure, all the time, but there's nothing big. In our orbit, we are the only large object. And for the purpose of this, moon is considered part of Earth because it orbits Earth. Does that make sense? So the moon is part of the Earth system as it is. So in our orbit, we're the only big thing. In Mars's orbit, it's the only big thing. In Mercury's orbit, it's the only big thing, so on and so forth. Pluto doesn't clear its orbit. Along its orbital path, there's lots of other big stuff. Really big, substantial asteroids, things like that. So its orbital path isn't clear. And for that reason, not because of size, not because of distance, not because of anything else, because its orbital path contains other things like it, other big celestial objects, for that reason, it gets downgraded to dwarf planet. Which was controversial, by the way. There were astronomers who were very upset about that. But that's the definition we use. And the same thing applies to Eris. Eris is big. It's spherical. We haven't taken good pictures of it yet. We haven't been there yet. But we know that it's big and spherical. It's heavier than Pluto. But it doesn't clear its neighborhood. There's other big things there. Yes?
Looking at this picture
Mhm.
here, it's that Eris Pluto, someone go out of the...
They go beyond the Kuiper belt. Yeah, so they go beyond the big asteroid belt.